Welcome to Part 3 of the normal sampling series on incremental sampling for radioactive waste. This segment presents two main topics, starting with the ISM Sampling Design. I'll discuss two conceptual tank models and show how SRS implements them today. We'll also examine the details of the Fundamental Error Management Plan and how the Savannah River National Laboratory interfaces with the ISM sampling program. Finally, we'll recap the videos and detail the benefits derived from ISM. ISM provides an impressive array of benefits that save both operational costs and radioactive dose to workers. As a bonus, we'll step back and see the impact of closing the first two tanks at SRS, reducing risks to the site, the state of South Carolina, and the nation. The DQOs established the fundamental error limit at 5% for each sampling phase. The next step is to examine the process for and the feasibility of achieving them, or a fallback position if the goals are not achievable. The matrix below contains results from a fundamental error sensitivity analysis which demonstrates the error goals are achievable. Before we examine the matrix, however, we need to review the fundamental error equation and discuss how it works. The equation has four terms, and we will see how the fundamental error is highly sensitive to two parameters, the sample mass and the maximum particle size. On the left side, we have the fundamental error. It is squared, it is a variance, and yields a percentage, that is, a relative error. Moving to the right side, we have C in the numerator, which is a sampling constant developed for environmental applications by Chuck Ramsey. It is a simple, unitless number equal to 20. This value is more complicated to calculate for mining applications, but is sufficient for the ISM application at SRS. The remaining parameter in the numerator is D, the diameter of the largest particle size anticipated in the residual sample material. D is cubed because it's a volume. As D increases, the size of the fundamental error increases in an exponential manner. The mitigating parameter is M in the denominator. M is the mass of the sample, which reduces the impact of the largest particle size. D and M are why we stress that both sufficient sample mass and minimum particle size are crucial components of sampling design. We also see here how the Smins principle is backed up by the mathematics. In terms of the anticipated tank particle sizes, we see the expected maximums will be between 0.1 and 0.05 centimeters, or 0.5 to 1 millimeter. The matrix presents the particle sizes in units of microns, millimeters, and centimeters because the SRS ISM document uses each of these units. The horizontal rows present the fundamental error for the particle size mass pairings. The masses appear on the right portion of the matrix, starting with 5 grams and increasing up to 70 grams in the left column. With a generic target of 15% error, along with a desired 70-gram sample mass, the table shows whether a particle size mass pairing produces an acceptable fundamental error. The fundamental error is optimally 5% for the initial incremental sample at SRS, as well as a 5% error for subsamples that might be taken at SRNL. The worst-case scenario is a fundamental error value of 17.9%, as shown in the 2 mm 5-gram pairing with the red highlighting. This result exceeds the generic level goal of a 15% fundamental error and is the only such exceedance in the matrix. The 15% fundamental error limit was considered a maximum fallback position if fundamental errors of less than 5% were not achievable. Pink shading highlights particle size mass pairings that exceed 5%. Only 4 instances occur, with none in the 70-gram column that represents the planned ISM sample. All matrix particle size mass pairings shown in either light green or dark green have fundamental errors below 5%. Note that within a mass column, as the particle size decreases, the fundamental error decreases rapidly, as predicted by the fundamental error equation. This emphasizes again the influence of particle size on the fundamental error. Similarly, the fundamental error decreases from left to right as the ISM sample mass increases. Honing in on the 70-gram column, our target ISM sample mass, we see that even with a particle size of 2 millimeters, the largest size particle anticipated, the fundamental error is 4.8%, just below our target of 5% for the tank sampling stage. In the cell below, for a particle size of 1 millimeter, the actual anticipated largest particle size, the fundamental error value is 1.7% and is comfortably below the 5% limit. For certain radionuclides, laboratory subsampling may be performed. This introduces another fundamental error by selecting a portion of the 70-gram mass to represent a single sample location. We chose a subsample mass of 15 grams that matched the minimum mass a robot might collect. The fundamental error results for a particle size of 2 millimeters is 10.3%, which exceeds the target of 5%. However, all fundamental errors for particle sizes of 1 millimeter or less fall below 5%. Past robotic sampling has collected reliably at least 15 grams of material at a sample location. Because an ISM sample is composed of 5 increments, the robots will collect at least 75 grams of material, which exceeds the minimum mass requirements. Therefore, this matrix indicates the probability of achieving fundamental error goals is high due to both small particle sizes and the sufficient masses obtained. Here we plug in the actual SRS tank numbers and masses to Pierre-Guy's fundamental error equation for a tank sample and a laboratory sample. The nomograph below shows the fundamental error occurs at every sampling and subsampling stage. We'll examine the fundamental error at the tank level as well as the fundamental error for a potential subsample at SRNL. The equation presents the calculation for the tank sample. On the right side, we put the sampling constant of 20 in the numerator, along with the largest particle size of 0.1 centimeter, or equivalently 1 millimeter, placing the 70-gram sample mass in the denominator. Solving the equation results in a fundamental error of 1.69% for a 70-gram tank sample, which confirms the 1.7 result we saw in the previous slide. Moving to the laboratory subsample fundamental error, we see the top portion of the equation remains the same. However, for the lab sample, we use the subsample mass of 15 grams in the denominator. This results in a fundamental error of 3.65%, which is more than twice as high, but remains below the target error goal and matches the value on the previous slide. Adding the tank and lab fundamental error variances and taking the square root, we obtain a total fundamental error of 4.02%, still below our goal of 5% error. Thus, our fundamental error goal is met for both the initial tank ISM sample and the laboratory subsample. Of course, the fundamental error is not the only error of concern. It is just one of Guy's 7 sampling errors. Discussing all the errors is outside the scope of this video. However, we will address briefly the grouping and segregation error. Note that 6 of the 7 sampling errors result from heterogeneity. The only exception is a preparation error, which is caused by items such as cross-contamination, material loss, sabotage, and other factors. Because of the turbulence created during tank pumping, mounds could have substantial stratification, which could come in many forms. The array of grouping and segregation conceptual models shown here stimulates the imagination on the possibilities and concerns. We can also see the grouping of random particles in the various I'm Peppy experiential models. Segregation by particle size, density, or inappropriate homogenization techniques increase grouping and segregation error further. Any one of these results and infinitely more could occur in a tank. The volumetric survey provides some input, but cannot provide a complete answer to the in situ heterogeneity. Core sampling could provide valuable information also, if feasible, with the knowledge gained available for use in future tank closure. This diagram and the next will present conceptual tank models for tank residual sampling. Both models appear in the 2015 SRS document on ISM implementation shown on the right. The first model is the simpler of the two, modeling situations where residuals are in a layer of equal thickness on the tank bottom. The legend in the upper right shows the 3 5-increment arrays we plan to create from the increments collected in the tank. The first array, shown in yellow diamonds, contains increments 1 through 5, which will be collected in a pentagonal pattern. The second array, shown in blue circles, contains increments 6 through 10 in a modified pentagonal array. The third array, shown in the tan squares, contains increments 11 through 15 in a polygonal array, with one sample placed either judgmentally or to account for access restrictions. A tank could contain any combination of patterned, random stratified, judgmental, access-constrained, or other components based on tank circumstances. The second tank conceptual model incorporates a design with two mounds, where Mound 1 is twice the volume as Mound 2. Mound 1 will contribute 6 samples, with 2 increments going to each of the 3 sample arrays. Mound 2 will contribute 3 samples, with 1 sample going to each sample array. The robotic crawler will collect 6 samples from the relatively uniform bottom layer, with 2 increments going to each of the 3 sample arrays. Although the mound and bottom areas each contribute 6 sample increments, the final masses apportioned to the ISM sample will differ due to volumetric proportioning as discussed in parts 1 and 2. Because the bottom layer contains more volume than the mound, the 2 bottom increments will contribute slightly more mass to the ISM sample. This cross-sectional view of the tank provides a different perspective on the mound conceptual model. Both mounds appear on the tank bottom. Because of the mound depths, core sampling at one or more locations may be used to extract mound material for sample increments. However, the sampling plant could use either a core sampler or the robot. The coring device brings the advantage of a more representative vertical profile of the mound, with the disadvantage of more awkward sampling using a 40 to 50 foot pole. In contrast, the robot offers easier sampling if it can access the mound, but is limited on the depth to which it can collect sample material. In the end, the physical access to the mound by the sampling devices could drive the decision on which sampling device to use. Hopefully, future robots will have the capability to collect core samples. Once the residual material is obtained, the ISM sample creation and laboratory work can begin. This diagram starts in the tanks and ends with the final ISM sample results. The tank farms send 3 groups of 5 separate increments to SRNL for what will become a single incremental sample. In total, 3 groups of 5 increments are sent to the lab. The laboratory processes the samples by drying, grinding, and blending the increments. The grinding process is not a necessity due to the inherent particle size, rather, it results from particle clumping that occurs during the material drying process. Once SRNL completes the sample preparation, the lab applies a proportional weighting algorithm to create the final ISM samples. The pink squares labeled 1, 2, and 3 represent the 70-gram samples. We expect the radionuclide concentration in these ISM samples to vary slightly, allowing us the opportunity to calculate a 95% upper confidence limit on the mean concentration of each radionuclide. Once we have the upper confidence limit for each ISM sample, the data are validated and become part of the waste tank residuals inventory determination report as seen in Part 1. Conceptual Model 2 requires 2 samples from Mound 1, 1 sample from Mound 2, and 2 samples from the floor for each sample array. This slide presents the details of how SRS calculates these sample numbers. The equation, which is equation 4 in the SRS SAP document, calculates the number of samples. It takes the ratio of the volumes of the various tank features to the total volume and then multiplies by 5. This calculates the number of increments in the ISM sample. Based on the ratios, this table confirms that Mound 1 requires 2 samples, Mound 2 requires 1 sample, and the floor material requires 2 samples. This process applies to each of the 3 ISM samples. Finally, the right column shows the Mound 1 and floor proportions are divided by 2 to accommodate the 5 increments needed for each sample array. The equation shown here uses the proportion of information from the previous slide to calculate the mass needed for each sample increment. The equation also incorporates a density factor. The sample material is assumed to have a density of 1 gram per milliliter, equating to an ISM sample mass of 70 grams. This normalizes the calculation, with all densities equal at the start. When the actual densities are applied, the calculated sample mass will be larger than 70 grams because all densities are greater than 1. As such, SRNL can choose to use increment sample masses that produce an ISM sample larger than 70 grams. At their discretion, they can also choose to adjust the increment masses to construct a sample closer to 70 grams. There is no issue in creating an ISM sample with a mass greater than 70 grams as long as the sample maintains the necessary proportions. For the Mound 1A increment, multiplying the proportions of 19.25 by 70 grams and then by the density of 1.36 yields a needed mass of 18.3 grams. Following this same procedure for the other 4 array increments and then summing the masses results in a mass of 96.4 grams. If each array increment contains sufficient mass, this almost 100-gram ISM sample may be created and analyzed. If incremental mass material is insufficient, the masses may be multiplied by 0.7 or other factor to obtain the smaller mass needed to create a 70-gram or larger ISM sample with the same proportions as shown in the column on the right. The final adjustment to the ISM sample is the volume uncertainty. As discussed in the Part 1 flowchart and the Part 2 DQOs, SRS applies a volumetric uncertainty adjustment to the ISM samples. Technicians provide a best estimate of the volume of the material in each tank domain, the mounds, floors, or other areas. SRS generates a random number from a triangular distribution that ranges from the low to the high volume estimated for that domain. SRS uses the random number as the volume for the corresponding tank domain to calculate the ISM sample volume uncertainty. The table shown here presents the calculations for Sample 1 in Conceptual Model 2. This process is repeated for each domain that will contribute material to the ISM sample. Next, SRS makes adjustments to the domain volumetric proportions. This table uses the randomly generated volumes from the last slide to calculate adjusted Sample 1 domain proportions based on the total domain volume. Each of the 3 domain volumes is divided by the total volume of 1,390 gallons. This obtains the proportion applied to each domain. This process is repeated for the remaining ISM samples 2 and 3. This table expands and summarizes the results of applying the volumetric uncertainty adjustments seen in the previous slide to all tank samples in all domains. The results from the previous slide appear here along with the corresponding calculations for ISM samples 2 and 3. SRS factors the volumetric uncertainty calculated here into the upper confidence level calculation for the ISM sample that goes into the residuals inventory report. The ISM innovation brought many benefits to the SRS liquid waste tank program. The benefits below pertain to operational and data quality aspects. First, we have field operations. We were able to maintain the business-as-usual paradigm with virtually no impact to field operations or procedures. Second is incremental mass. A discrete sample needs 70 grams to achieve the lab quality goals. ISM only requires about 15 grams per location, which is virtually always achievable. This ties into the next benefit of reduced risk. The 70-gram goal is more achievable with ISM and reduces the risk of missed detection limits during the sample analysis. Next, better data. ISM and the SMINS principle managed the variability and error, providing estimates closer to the true sample mean, simultaneously reducing variability and uncertainty on the final radionuclide concentrations. We also achieved increased representativeness. Proportional weighting and density weighting incorporate additional components needed to represent the tank material more accurately. And finally, we have improved parameters. The performance assessment benefits from the most accurate data possible, and ISM helps to ensure accuracy. The benefits below pertain to laboratory and programmatic aspects. First, we have lower costs. Using ISM requires fewer sample analyses at the Savannah River National Laboratory. At $1 million or more per sample, ISM lowers lab costs dramatically. Second, we have shortened turnaround time. ISM allows SRNL to introduce efficiencies into the sample analysis process and workflow. Third, we have ALARA benefits. With fewer samples analyzed, the tank farm contribution to lab worker dose was reduced, achieving ALARA goals. Fourth, we have programmatic benefits, which come in the form of faster regulatory acceptance, which is always welcome. Next, we gained schedule shortening with compressed workflow in both the field and the laboratory operations. And finally, lean benefits. ISM made sample material collected during previous tank sampling efforts available for use if necessary. Closing the first high-level waste tanks, tanks 17 and 20, even without ISM, represented a major accomplishment and DOE celebrated. The upper left photo shows Dave Olson on the left, then president of Savannah River Remediation, along with Dave Moody on the right, at that time the SRS site director. The lower photo shows Thomas D'Agostino, then DOE Undersecretary, on the left, Catherine Templeton, then SC DHEC Director, in the center, and Lindsey Graham, South Carolina Senator to the United States Congress. ISM techniques have assisted in closing 6 additional liquid waste tanks at SRS. DOE and SRS continue to bring additional innovations to the tank closure process that reduce and will eventually eliminate South Carolina's largest environmental risk. Thank you for watching Part 3 of the Normal Sampling series on incremental sampling for radioactive wastes. I hope you enjoyed the series. I encourage you to enjoy more normal sampling videos at our site and subscribe for upcoming videos. I also encourage you to contact us for information on experiential sampling using the ISM physical models you see behind me. Thanks again for watching. See you next time on Normal Sampling.